In this tutorial I'd like to talk about the electrophilic substitution in arenes, and if we begin with the basic mechanism, we'll take our archetypal arene, and that will be benzene, and our electrophile we'll just give the generic name E+, so we see it's electron deficient, it's attracted to electrons. So we have our structure of benzene, where we have this concentration of negative charge with the delocalized electrons in the centre. And here we have our electrophile approaching the benzene ring. So in our first case, these electrons from the ring are attracted to the electrophile to make a bond with it. This gives us an intermediate where we have partially lost some of the delocalized structure of the ring. But of course, one of the really characteristic things about the chemistry of the arenes is the stability of this benzene ring. So what happens after this intermediate is the electrons from the hydrogen go back into the delocalized structure, giving us back the arene structure, the delocalized structure of the ring. The electrophile is still attached, and we have lost H+ from the ring. So let's look at a specific example. We'll look at nitration of the benzene ring. So in order to nitrate a benzene ring, we would use concentrated nitric acid, HNO3, and concentrated sulfuric acid, H2SO4. And these two acids together will generate the electrophile that we're looking for, which will be NO2+. So we can draw the mechanism for this reaction, where we have our benzene ring with the delocalized structure, our electrophile NO2+, and the electrons from the ring come out to bond with the NO2, giving us an intermediate structure with the NO2 attached, as well as the hydrogen, and we have only partial delocalization in the ring. So for the next step, the electrons from the hydrogen go back into the ring to give us back the stability of the benzene ring, and we have this back with the NO2 is still attached, where we have nitrobenzene, and now we have the hydrogen ion as the other product. This is a very basic representation of the mechanism that's going on here. There are layers of complication to it, some of which I'll explain shortly, so check the requirements of your course. This may be all that you have to be able to draw. But do have a look at what happens when the benzene ring is already substituted and we have a different arene. And phenol would be an example of a substituted arene that you might have studied. And here we have the structure of phenol. So we find that phenols are more reactive than benzene itself. And if we want to nitrate a phenol, we can use dilute nitric acid rather than concentrated with concentrated sulfuric acid. The the electrophile that we generate is the same, that's doing the reacting, NO2+. So here we have a similar situation where the electrons from the ring come to make the bond with the NO2+, and we get some intermediates. And in both cases, the hydrogen puts its electrons back into the ring to give us back the delocalized structure and the stability of the benzene ring. This gives us two products. So we have 2 nitrophenol and 4 nitrophenol. So we have 2 different isomers of the nitrated product. Your course may want you to recognise that you could have these 2 products without necessarily asking you to explain why. But in the rest of this tutorial, I am going to explain why the substitution happens in the 2 and the 4 position. So in order to explain the products, I'm going to use the Kekule structure because they're more helpful here rather than the delocalized structure. So I'm going to start with one Kekule form and show how it might move through different canonical forms to the other Kekule structure. And if we start with the lone pair of electrons on the oxygen, they might, still being in p orbitals, interact with the ring. And of course, as soon as they move to interact with the ring, these electrons here would move because they would be repelled. So if we could freeze it just after that movement, we would find that we would have this structure here with a negative charge sitting on this number 2 carbon and still the other 2 canonical forms. Of course, if we continue the movement around the ring, these electrons can then move into the ring if this bond is broken, which gives us the possibility of another form where we have a negative charge localized on there. We have this form here, and still the oxygen, having formed an extra bond, donated its electrons into the ring, having a plus charge. Again, carrying on with the movement, this electron can move there, causing this one to move here, and we might freeze that for just another moment, giving us another canonical form with a negative charge located there, and the double bonds here, and still the double bonds OH plus. And the last step in the movement, these electrons moving back into the ring, and this bond's breaking to give oxygen back its lone pair of electrons. So we have at the end phenol with the other canonical form compared with the one that we started with. What's interesting to note, during this process of this movement, we have negative charges localized in the 2 and 4 positions on the ring. And if we were just to take perhaps maybe this one here with a negative charge located on the 4 position, and then have our electrophile in there, we can see that this might make the bonds here, and this is why we would get the NO2 at this point in this transition, if you like, or this canonical form, and then we would have the rest of it happening as normal, where that comes in there, and then that would move round, forming the rest of it, this one here, and then back to the final product through the other canonical forms, but this time with the NO2 attached here. So it's these forms that show us why, if we have a substituted arene, it can attack the ring at the 2 and 4 positions to form the 2 and 4 products that we talked earlier. It is also important to note that it is the interaction of that lone pair of electrons from the oxygen. This interaction activates the rings, or the ring for electrophilic substitution. This is a really good phrase, activates the ring, it really turns it on for electrophilic substitution, and this is why we find that phenols will react a lot more readily than benzene will. And indeed, sometimes we see them substituted in more than one position. So we will see multiple substitutions depending on what the reaction conditions are that we use. We also find a similar process going on for phenyl amines, where the lone pair in the nitrogen can activate the ring in quite a similar way, making it more reactive and more susceptible to multiple substitutions and substitutions in those positions. So do check your course. You're probably not required to be able to draw out all the Kekule structures and the detailed mechanism, but offered here purely as a means of helping you understand what is going on, and for most cases the basic mechanism may be enough for what you actually need to be writing down.